of Weather Live. My name is Justin. So in our show today, we're going to make a giant cloud. How's that sound, everyone? Sounds good? Yeah. Now, before we get to that point, there are a couple things we're going to discuss and do a cool experiment with, okay? The first is air, okay? We're going to do a few cool experiments to show you how powerful the air is, okay? After that, I'm going to show you a couple experiments involving water and how water affects the weather as well. You guys feeling a little wet now? Yeah, all right, very good. This is how I keep people awake during my shows, too. So no dozing off. Now, question for you. How many of us feel like we're being squished by the air right now? Okay, it doesn't seem like anyone's feeling squished by the air. Well, long time ago, this crazy German dude by the name of Otto von Guericke had this idea that air was powerful, okay? People in his era in Germany in the mid-1600s did not believe him, and they called him an airhead. So they said, if you think the air is all heavy and powerful, prove it. Here's what Mr. von Guericke did. He took a sphere, his about the size of a beach ball, ours was about the size of a softball. But what he did with the sphere was he cut it in half, put the two sides back together, and then vacuumed most of the air that was inside the sphere, okay? So right now we have air inside the sphere, and we have air outside the sphere. He changed that by pulling out the air from inside, but keeping the air on the outside. Then he tried to get people to pull the two sides apart. They could not do it. So then he got together the biggest, strongest horses he could find. He started with 2 horses. Let me ask you guys, do you think 2 horses could pull the 2 sides of the sphere apart with little air inside?
No.
They could not. So he went to 4. What do you guys think?
No.
Nope. What about 8?
No.
Nope. 12?
No.
16?
No.
Actually, yes. It took 16 powerful horses to pull the 2 sides apart. So what we wanted to do today was replicate that experiment von Guericke did some 400 years ago. We have the spheres, we have a vacuum, but I think we might be missing something. What are we missing?
Horses.
Yeah, those horses are a little bit unavailable right now for our experiment. So we'll have to do this experiment with humans. So humans, who would like to give it a try? We are going to start with ladies first. Ladies first. How about you over here in the white jeep? And how about you in the back? Come on up. What's your name? Ivana. Come on over here, miss. All the way in the back there. What's your name? Lillian. Lillian, I want you to come on over here, stand right here. Now, Ivana and Lillian, I want you to prove there's nothing to it. Pull the 2 sides apart. All right, now, everyone, do we think it'll be just that easy when I take the air from inside of the sphere? No. Let's find out. So, we have here a vacuum. This vacuum is able to pull out about roughly 80% of the air that is inside the sphere. Now, is there any air in outer space? No. No, so do you think the ladies could be able to pull the 2 sides apart if they're in outer space?
No.
They should be able to, right? Because the air pressure would still be greater inside of the sphere than outside. But it turns out we have a lot of air pressure surrounding our sphere. So we're just going to see how difficult, how challenging it'll be for our ladies to pull the 2 sides apart, okay? So, ladies, on your marks, get set, pull! Look at this tug of war! Wait, wasn't that? Oh wait, we were supposed to be a tug of war. We're supposed to pull the 2 sides apart. All right, here we go. Give you a few more seconds. Give you 3, 2, 1. All right, well, that was a heck of a tug of war, but unfortunately the 2 sides are still together. Well, that's all right, ladies. Go back to your seats. Let's give the ladies a big round of applause. Gentlemen, now is your opportunity. Who would like to give this a try? Let's take a look. How about you right here? How about you jumping? Because you look really excited. Your name is?
AJ.
Your name is? Jalen? Okay, AJ, Jalen. Now AJ and Jalen are going to help us prove one of 2 things. Either that, yes, indeed, air is heavy and powerful. Or they might help us prove something else. Something that has absolutely nothing to do with weather. that boys are stronger. Okay, gentlemen, are you ready? On your mark, get set, pull. All right. Yes, great job. You go back to seat. Let's give AJ and Jalen a big round of applause. Thanks for your help, bud. All right, so then we just proved the age-old question that boys are stronger. Let's do it this way. If you think we did prove that boys are stronger, please indicate by raising your hand. Okay? Okay, very good. If you think we did not prove that boys are stronger, please indicate by raising your hand. This vote seemed to have went by party lines. So, ladies, please tell me why you think that we did not prove that boys are stronger.
Because you put air into it.
The professor said that we put air in the spheres here. Is that what I did?
Yeah.
They caught us. We're busted. Yeah, I know. I'm sorry. So it's not that air is, or it is indeed that air is heavy and powerful. It's not that boys are stronger. I'm sorry, guys. But this does show us again that air is heavy and powerful. But you're probably wondering, what does this have to do with weather? Well, let's take a look. What I'm going to do next is take this balloon here and fill it with air, okay? I'm going to try again. And we're going to put a little bit more in here. Okay, so right now, this balloon is filled with rather mild air, okay? Rather warm air from my breath. What I'm going to do is take this balloon and submerge it in something very, very cold. How many of you have ever seen liquid nitrogen before? Most of us. Pretty cold stuff, right? Anyone remember how cold liquid nitrogen is? What the temperature of it is?
Negative 320.
This gentleman's got it. Negative 320 degrees. Okay, that's Fahrenheit. Okay, very, very cold stuff. So what do we suppose is going to happen to our balloon when we submerge it in a liquid that's 320 degrees below zero? Start with you.
It's gonna all the air.
Okay, this young professor thinks that we are going to, the balloon is going to depressurize. Okay, any other guesses? Yes?
It's gonna shatter.
It's going to shatter. Okay, that's possible. Yes? Okay. Pop. Any others? One more maybe? One more. Yes, ma'am. It'll blow up. I like that thinking. All right, here we go. Let's give this a try. I'm going to, for my safety, put my gloves and goggles on, and we're going to see what happens what's going to happen to our balloon. Can I get a professor to come up with me here? Let's see here. Who hasn't been up yet? How about you right here? Come on over. Stand up here on the stage with me. What is your name? Abby. Abby, are you full of hot air? Just say yes. Okay, Abby's full of hot air. That's what we're going to use. Okay, Abby, stay put for a second. Here's our balloon. Okay, let's go ahead and submerge it in our liquid nitrogen. Here we go. All right, so that balloon is starting to get very, very cold. The air inside is going to get very, very cold. You say your name was Abby, right? Okay, so I'm going to have Abby blow some warm air to warm up that balloon. In just a second, I'll let you guys see what happens, all right? So here's our balloon.
Whoa.
Abby, go ahead and blow that warm air. Look at what's happening.
Oh, that is cool.
Excellent.
Oh.
What's the again? Okay, we'll do it again. You have more hot air in you, right, Abby? Okay, very good. So we're submerging that balloon in liquid nitrogen. Okay, that stuff is very, very cold. The air inside of there is getting very, very cold. And when that air inside of our balloon gets very, very cold, it wants to bunch up. Okay, and that's causing our balloon to get smaller. Does the air actually escape the balloon? No. It does not escape the balloon. That is correct. Okay, Abby, work your magic. Oh, that's pretty cool. Look at that. Very nicely done, Abby. Go back to seat. Let's give Abby a big round of applause. Thanks very much. Question for you. What would happen if instead of this being liquid nitrogen, what if it was hot boiling water? Could pop.
Expand.
Could expand, that's right. So if we make the air in there warmer, that balloon expands, okay? This is the whole reason why cold air sinks. What does warm air do? Rise, yeah, absolutely. So, of course, there is one gas in our air that drives all of this weather, okay? It makes up a very, very small percentage of our air, but it's what causes our rainy days and our snowy days. Which gas am I talking about? Anyone know? Not oxygen. Do you know what it is? Not quite sure? Do you know what it is? Not quite carbon dioxide. It does make a small percentage of our air. You know what it is?
Nitrogen.
Nitrogen. Good guess. I'll give you a hint. It starts with water.
Hydrogen.
Water. Very good. Yes. Turns out, water vapor doesn't just magically find its way into the air. Does anyone know how water vapor gets into our air? Yes. Water evaporates. How does water evaporate? Professor? Well, we'll talk about that. You know how it evaporates? What was that? Heat. What gives water heat?
The sun.
The sun, yes. So the sun shines on the water. Most of our world's water comes from the oceans, and what happens is it warms that water vapor or water into a gas, and that gas is warm. And what do we know about gases when they get warm and our air when it gets warm? It goes up. And up there in the sky, is it warmer or colder? Very cold, right? So what happens to that water vapor when it gets cold? Turns back into water, right? It condenses back into a liquid, okay? And then eventually that water vapor gets so heavy, or that water gets so heavy it falls down as rain. If it's really cold, it turns into snow, sleet, and other stuff, okay? What I'm going to show you is what happens when that water vapor gets cold. On this hot plate, I boiled a little bit of water. Okay, do you guys see the steam coming out?
Yeah.
And we're going to dip the can full of very hot water vapor in this bucket of cold water. And we're going to see what happens. Are you guys ready for this?
Yeah.
Okay, now, this is going to happen very, very quickly. Okay, I'm going to do this experiment twice. Both times, try not to blink when I count down to 1. Okay, so we're going to do a countdown from 5. Don't blink when we get to 1. Here we go. 5, 4, 3, 2, 1.
What? I didn't get that.
Now, you want to see something cool?
Yeah.
This is how much water I put into it originally. That's kind of weird. Show it to you again. 5, 4, 3, 2, 1. So, I'm curious about something. How did we get more water come out of the can than I put into it? Anyone have a guess as to why? You have a guess? The can crushed it. That played a role. Because what happened, that was the most obvious thing, right? Our can crushed. And what happened was the pressure from our air was much greater than the pressure that was inside of our can. And because of that, it acted as a vacuum, okay? So basically, this water vapor, or the water vapor changing into water, dropped that air pressure and turned it into a vacuum, pulling in, sucking in water from the bucket, okay? Now, storms are only, what they are is just water-driven vacuums, okay? They're powered by water. And one of the most biggest violent storms I can think of are those big swirly things that happen in the ocean, especially late in the summer. Hurricanes, yes. What's in the center of a hurricane? The eye of the storm, that is right. And inside the eye is a giant vacuum pulling in air and pulling in more water. And what happens when you get air moving? What happens? Wind, that is right. The wind damage in a hurricane can be deadly. What I'm about to show you guys is the effect of a Category 2 hurricane, winds of 100 miles an hour. Here we have a block of wood. How many of you live in a home that's made out of wood? Raise your hand. About half of us. I do too, okay? We're going to see how well our home holds up to this. Here I have a pencil. This is going to represent debris that's in the midst of our storm. And we're going to make this pencil travel at about 100 miles an hour, which is a rather kind of average hurricane that we might hear about hitting the coast, okay? So, here's what I'm gonna do. We have our block of wood right here. And I'm gonna take this pencil, and we're gonna see what happens. Everybody ready? All right, here we go. I'm going to do a countdown. And when we get down to 1, do not blink. All right? So here we go. From 5, 5, 4, 3, 2, 1.
That was fast.
That was pretty fast. Let's take a look. How well did our... Oh, my. Goodness.
Oh, man.
That's pretty impressive, folks. Would you want to be inside your home during a hurricane?
No.
No, this is why they tell people to get out of the way when one of these storms hit, okay? And of course, how many of you live here in Ohio? Almost all of us, yeah. Well, here in Ohio, of course, we do not see hurricanes. We are not near that source that gives hurricane energy, that warm ocean water. But there are other storms out there that can give us winds of 100 miles an hour. What kind of storms do you think I'm talking about? Just shout it out. Tornadoes. Just like how this is a pretty average hurricane damage, tornadoes give you 100-mile-an-hour winds quite often as well. So this is the kind of damage you could also expect inside a tornado. That's pretty damaging as well. All right, now has come time for our grand finale. What are we going to do for our grand finale? We're going to make a cloud, that's right. Now I get asked all the time, you know, Justin, where can you get a cloud maker, right? Well, here's our cloud maker. You can get them at Lowe's, Home Depot, Walmart. They're pretty inexpensive. Making a cloud is as simple as making a peanut butter and jelly sandwich. All we need are 3 basic ingredients. And I'm sure everybody in this room knows the ingredients in a peanut butter and jelly sandwich. Just shout them out for me. Yes, bread, peanut butter, and jelly. Now, I know what this fellow here in the second row is thinking. I know what you're thinking, sir. You're thinking that, wow, it'd be great if clouds are made out of bread, peanut butter, and jelly, right? Because it make foggy days really yummy. And you can make some scents of Prince's Purple Rain salt. But it turns out clouds are not made out of bread, peanut butter, and jelly. They're made up of 3 other very basic ingredients. Can anyone name one of them for me? Water is 1. What else? Air is 2. There's 1 more. I think I heard someone say it. Dust. Yes, very good. Water, dust, air. Now, let's go back for a second. Does water just find its way magically into clouds? No, I can't just go poof, there's water in the clouds. How does it get up there? Evaporation, right? How does water evaporate again? Heat. Yes, from the sun, but of course we don't get much direct sunlight in this room. So instead, I just have some really hot water from the tap. Very good. So we have our hot water. Secondly, we need dust. Okay? We have a lot of dust in this room because I haven't vacuumed in here in several days. So, what you guys can do for me is kick up a little bit of that dust and bring that dust this way. So just kick it up for me. Yes, you guys kick it up as well. Excellent, thank you very much. One more thing we need is... What was the other ingredient? Air. Yes. Now, correct me if I'm wrong, but don't we already have air in this room? Yes. Yes, otherwise we'd all be feeling rather blue. Okay. So, why do we not have a cloud?
There's no air.
No, there's air.
Because it's not cold enough.
What was that?
It's not cold enough.
That's right. The biggest difference between the air down here and the air up there, air is much, much colder. As a matter of fact, during big, powerful storms, sometimes the cloud temperatures can reach 70 degrees below 0 Fahrenheit. So how about we make it that cold in here? How's that sound?
No.
A little too cold for my liking. Well, we have a solution to this.
Liquid nitrogen.
Remember that really cold stuff we had earlier in the show?
Yeah.
Turns out, it is very much like the air, because it is made from the #1 ingredient of the air. The #1 ingredient of our air is, its name starts with an N and rhymes with nitrogen. What do you think it's called? Nitrogen, yes. This is liquid nitrogen, okay? Now, this stuff again is 320 degrees below 0 Fahrenheit. Cold enough to make a cloud, right?
Yeah.
Absolutely. The best part is it won't stay a liquid for very long. The second that liquid nitrogen is poured out of our container here, it will start changing back into nitrogen gas, the same stuff that makes most of the air. Now, do you suppose that that gas is going to be warm or cold? Very, very cold. So it's going to act very much like the cold air that is up in our cloud, okay? Now, before we do this, a couple of safety things. As I'm pouring this out and making our cloud, that bucket will be very close to 320 degrees below 0 Fahrenheit. Yes, I would not want to touch something that cold, okay? So please stay where you are until I say it's safe to get up and move, okay? Everyone understand that? Okay. Secondly, I know some of you will walk by this bucket and you'll want to touch a cloud, and that is perfectly okay. Just make sure that you do not stick anything more than your hand into the bucket, simply because there could still be some liquid nitrogen down the bucket even several minutes after I make a cloud. Everyone understand that? Okay, very good. Now we've got all out of the way, let's make our cloud, okay? Now, since this is the coolest experiment in COSI, quite literally, it deserves the loudest and longest countdown. So let's give it a nice big loud countdown from 11. Okay, so here we go. 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Touch the cloud. Put it in your pocket. Take it home as a souvenir. Very good. It's safe to get up, everyone.
All right, guys, stay close.
And